you will tell us about exotic state at age 73.
This morning, I'm very happy to come here to present our recent progress on the exotic hadron states. And a few of the audience here may have already listened to my talk. So previously, I want to discuss the heavy flavor meson decays based on my collaboration with Castillejo-Dalitz-Dyson and also Professor Xian Wei. But then I found my topic discussed here is more relevant to the one discussed in this morning, especially for the Professor Eric Bratton and also Oki. I will use these two particles as examples, the ZB states and the X3872. In the first part, the only input is the pole position. And in second part, you will find some new surprise beyond the conventional virtue or bound state. As we know, more and more exotic hadron state candidate XYZ states are observed in experiment. And their interpretations are still mysterious. So many scenarios have been proposed, like the molecular, hybrid, or kinematic effects. And the most prominent one may be the molecular states, because we notice that these XYZ states typically stay close to threshold of meson pairs, around 2 or 3 MeV. For example, for the ZB above B bar threshold. So in principle, the effective range expansion works. And for ZB states, the PDG has already determined these quantum numbers, and isospin, G parity, and the total spin, and the parity. Okay, in this page, I only want to show the last 2 points and neglect these details. I want to see that the very simple model, the uncoupled channel effective range expansion, works at least as a first approximation. Because in experiment, the Bell has measured ZB to BB bar, the branching ratio is around 80%, only single channel. Okay. Now, in the effective range expansion, there are 2 quantities. One is a length of A and here, and the other is the effective range R. And for the resonance, the mass and the width can be also provided. So there's the 2 correspondence. You can solve the equation of A and R to reproduce the pole position. And then we can get these values of A and R. And these numbers are the uncertainties estimated by us. And although this model is very simple, but we want to mention that on one hand, it reproduces the pole position, and on the other hand, it can describe the data near threshold. And our selling point for this paper is the concept of the compositeness. The whole story should be dated back to 1960s. That's for the well-known relation for the deuteron. And if it is a pure bound state, the wave function generalization should vanish. And Z is called the elementariness, and X is called compositeness. And it's defined as in this way. And gamma is the residue. G is a 2-point loop function. And okay, and here if x equals 0.8, it means the 80% of that b is the b star bar components. And as in the last talk of Oki, he has mentioned the bound state appears in the first Riemann sheet, and for the resonance it appears in the unphysical Riemann sheet. So here, if you want to calculate gamma, the residue, you need to be careful. And however, for resonance case, if you want to calculate x in this way, you will find it's a complex number. Now, what to do next? We find that by making a phase transformation, we can redefine x in this way. But we have a condition that the ER square larger than the lightest here energy threshold. And in our case, the effective range expansion, we can adapt it to the non-relativist case. And we know that at the pole positions, the momentum is also complex. We have a real and the imaginary part. And here we have the A and R. And in experiments, they can provide the mass and width. So all these relations can be related to each other. Here is our value for the x. For the ZB state is around 80%, and for ZB prime it's around 70%. And here we make a big caution that a distinct feature for the effective range expansion is that, and here the effective range is in the neutral size. The neutral size means the pion exchange energy scales is around 1 Fermi, and here it is just so. But in some cases, the effective range will be huge. In that way, we will doubt the convergence of effective range expansion. So we notice that there's a more general two-body scattering amplitude. It is not invented by us. We should admit that. But first used in the XYZ states. Here I use a few words to explain how the CDD pole appears. The CDD pole is named after the discoverer, Dalitz-Dyson and the first guy. You should learn of the words the crossing symmetry, analyticity, and unitarity. That means that there's a theory in the 1960s in Berkeley, like the very famous guy Jeffrey Chu, right? Before the quantum field theory. And you can implement all the quantities in the n over d method in dispersion relation. And in the n function, you have the left-hand cut. And in d function, you have right-handed cut and the poles. But before the dynamics of theory, there's ambiguity of the poles in d function. So it's here, you should implement the CDD pole. And in other words, in modern language, we can understand it better. This is done by Dyson, because the CDD pole is very important to distinguish the elementary and the composite particles. If CDD pole is very close to two-body threshold, it will result in a very small compositeness. In this way, we will see that it contains many other important components, like the compact quark-gluon states. If CDD is very far from threshold, you will get a large compositeness, like 0.8 or 0.9, as we shown before. Then it means it contains a large portion of two-meson constituents. It's still hard to understand this. I will say that the CDD pole is a zero of amplitude of t. Because you see, if E equals mCDD, here will go to infinity. And 1 over infinity is 0 of t. At that point, is the manifestations of the elementary particles. At the last two points, we show how it is related to effective range expansion. We just expand the real part, we can recover the ERE. At this point, you will see if CDD is close to threshold, the value of effective range will blow up. So, and certainly here's the expansion does not converge. I will extensively use this amplitude, or you can see it's a new parameterization of two-body scattering amplitude. We will apply it to the XYZ states. The X3872 particle is the first observed one in experiment, and it deserves our great deal of efforts. In 2003, Bell observed it, and now, up to now, it has already 1,400 papers. And the PDG has determined these quantum numbers also very well. And from now on, we will define the energy with respect to DD bar threshold. And concerning its interpretations, as I already mentioned, it may be a molecular-like virtual state or bound state, or even pre-existing state. That means elementary, or the CC bar quaternion. Typically, these virtual or bound scenarios are based on the ERE analysis. The pioneering one is done by Hanhart, and also including Bratton. And here and in his paper, there's a concept error. It is pointed by Bratton. But as we mentioned that, if there's a nearby CDD pole, the ERE convergence will be dot. And we have shown this here, right? So if we use the new parameterization of two-body scattering amplitude, we will find beyond the conventional virtual or bound state, we will have a simultaneous virtue in second Riemann sheet and a bound state in first Riemann sheet. And also we find maybe there's high order S matrix pole. It is allowed by general S matrix theory, but not observed in the world. Before our analysis of the data, I will briefly review the experimental situation. And here's the D star data for the Baba and Bell. We also have Gypsy Pi data, Baba and Bell. And in this case is the PP Barclaysm from CDF. All the previous analysis do not include this data set. And also this data set has very high statistics because it's around 1 MeV. Okay, for experimental mental situation, we have the 2 data sets of D star bar and 3 data sets of Gypsy Pi. And we have shown that there's a new parameterization of two-body scattering amplitude. And here I again confirm that if CDD bar, if the CDD pole is very far, such that it can be neglected, you will recover the zero range effective range expansion that is extensively discussed by Eric Bratton. For fitting the data, we will use the D function. Okay, now we define a spectrum function. That is defined in this way. And the alpha is the residue of the D function, and the gamma x is a very small width of the pole position. You will find the right side is just a Breit-Wigner-like. So if it is a narrow resonance or the bound state, the integral is very close to 1. Otherwise, it's not. For example, if the shape div is the Breit-Wigner match, like the volatile state, you will not have this constraint or relation. And for the ERE relation, the integral does not convert, just cut off in the signal region. Here, you will find it's 1 over k. Because our data set is the measured event distribution. So now we also provide our formula for that. This is for B2 gypsy pi decay channel. And the NBB bar is the total BB bar numbers. And the capital BG is the overall normalization constant. And the CBG is the background. We just use linear background in the short region. And here's R function is the Gaussian resolution function used by experiment. Here we also include the beam width effect. That is, all the experimental details are also considered by us. And for PP bar to gypsy channel, you just replace this event number by the partial cross sections. And here is a more complicated form for B to D star. It's first derived by Bratton, but in our paper we have more elaborate the details. Without mentioning it too much, we want to say the 2 points. One is that you can understand it by comparing to the previous one. If the gamma star is the D star width, it's very small, right? This around 60 keV. If this guy goes to 0, you will have a delta function. Then you will recover the previous equation. But now the D star width is important because although it's very small, note that the X particle locus is also 0.1 MeV. It's not so small compared to the location. And in numerics, we also confirm this point. Okay, now we show how we fit. That's as I mentioned, these 2 overall constants and the background are fitted parameters in any case. And if the integral is 1, then the overall constant can be justified as a branching fraction. And in the D function, we only want to make a comment. Maybe one can use the more general D function other than the ERE. In the D function, there are these parameters: the CDD pole and its residue, and the subtraction constant beta. We find it may be redundant for fitting to reduce the correlation between parameters. Then we make these choices. For the first case, we just use the ERE, but making a combined phase. We want to do that because 2 purposes. The first is that we want to confirm our code works. The other one is the combined phase can constrain the parameters more stringently than then the fit one by one. In the second case, we impose a virtual state or the bound. In any case, I want to make my language very simple, like that. We want to provide some relations to constrain the parameters. In the third case, there's a simultaneous virtual and bound state. Okay, now it's the result of fit. It is hard to distinguish in the JPSI-PyPy channel. And for DD star channel, it's also acceptable. But still there's difference near threshold. And here we list our numerical values for the populations and the compositeness and the residues and also the observed event numbers. The last line can be related to branching fraction by dividing the overall the total event numbers. In the first case, because we use ERE, it's a pure bound state. The compositeness is 1. And in second case, here is a double virtual state. And here is a triple virtual state. It means in the vanishing width of D star, these two poles converge together. And for the third case, it's a simultaneous virtual and bound state. In this case, you find the compositeness is very small. And here around 10%. It is more likely a pre-existing state. So that's we want to mention these 2 points again. If we want to use a more advanced treatment, we will get the new results. In the case 2, we find the higher order asymmetric pole. And so these residues are very large. And in the third case, we find in both the first and the second Riemann sheet, there are poles. And also CDD is close to threshold. The resulting compositeness is very small. We also find that this conclusion agrees with Morgan. Morgan is a collaborator of Panington in GLab, right? And the Morgan criterion states that if there's a pole both in first and second Riemann sheet, the compositeness is very small. Most probably, it's a pre-existing state. In our case, we quantify this case is around 10%. Okay, I think now finished. I want to save 2 minutes for the lunch. Thank you.
For questions. No questions? You want to have lunch earlier? Okay, if not, let's start to speak again. And as we already heard, the lunch boxes are provided at the NCTS with in different buildings, so please follow the local people. And please be back here on time at 1:30.